Welcome to another deep dive. Today we're going to be looking at
Oh, yeah.
this really cool paper
Okay.
called Attention is All You Need,
I love this paper.
and it's by some folks from Google.
Uh-huh.
And it introduced this concept called the transformer model, which is kind of taking over AI.
Absolutely.
And I think this is one of those papers that was kind of like a paradigm shift
Yeah,
in how we think about AI.
definitely.
So I'm excited to jump in and kind of unpack it with you.
Sounds good.
So the paper starts by talking about recurrent neural networks,
Yes.
or RNNs as they're known.
Right.
And they talk about some of the limitations of these RNNs, and particularly with dealing with these longer sequences of data.
Yeah, they struggle with that.
Yeah,
It's like,
they have a hard time remembering things,
yeah, if you were to read a book
right?
and try to understand the last chapter
Yeah,
only by remembering
Yeah.
one word at a time,
exactly.
that would be very difficult.
It would be,
Right. That's basically what RNNs are doing.
yeah.
Yeah. And so what the transformer does is it does away with that whole sequential processing thing.
Okay.
It says, we're not going to do that anymore. We're going to just look at the whole thing, and we're going to use something called attention mechanisms instead.
That sounds much better.
Much better.
So what are these attention mechanisms?
So attention mechanisms allow the model to
Yeah.
focus on certain parts of the input that are
Yeah.
most important.
Like actually pay attention.
Exactly.
That's so cool.
Yeah.
And they were able to do this at Google. No wonder it's such a big deal.
Yeah, Google's got a lot of resources.
Yeah.
They do.
So this transformer model that they're introducing
Uh-huh.
uses these attention mechanisms instead of these RNNs.
Right.
What makes that so special? What's the big advantage?
Well, for one thing, it allows for much more efficient processing, especially when it comes to those long sequences we talked about.
Right.
It can look at the whole input at once, make connections that RNNs just couldn't
Yeah.
because they were so focused on just that one word at a time.
Yeah, it's like the difference between reading a whole paragraph
Yes.
to understand a sentence
Uh-huh.
versus just looking at each word individually.
That's a great way to put it.
Yeah.
Yeah.
So they were able to get some pretty amazing results
Yeah.
with this.
State of the art. They got state-of-the-art performance on machine translation tasks,
Wow.
beat previous models by quite a bit.
Okay.
And they did it all with less training time
And less.
and less computational resources.
Wow, that's really impressive.
Yeah, it's pretty cool.
So let's dig into this attention thing a bit more.
Okay,
Can you unpack that for us? Like, what does that really mean?
sure. So in the transformer, they use something called scaled dot product attention.
Scale dot product attention.
Yeah, basically what it does is it calculates a score for how relevant each word in the sequence
Okay.
is to every other word.
So every word is compared to every other word.
Every single one.
That's a lot of computation.
It is
Wow.
a lot of math.
So that gives it this like really comprehensive
Yeah.
understanding of the relationship
That's exactly right.
between all the words.
Yep.
Okay, that's fascinating.
So it's analyzing the sentence from all angles at the same time.
That's crazy.
Yeah.
So we had these scores, right?
Yep.
That tells us how the words all relate to each other.
Mm-hmm.
What happens next?
So to make things even more complicated,
Oh, what? Why?
they use what's called multi-head attention.
Multi-head.
Multi-head attention.
What's that?
It's like having multiple spotlights
Yeah.
shining on different aspects of the sentence at the same time.
Multiple spotlights.
Multiple spotlights.
Okay.
So you can imagine one spotlight
Um,
focusing on the grammar,
Okay.
another spotlight on the meaning,
Uh-huh.
and yet another spotlight on the overall context.
So it's like a team of experts,
Exactly.
each with their own specialty,
Yeah.
analyzing the sentence.
Exactly.
That's pretty cool.
Yeah, it is.
Okay, so you've got these spotlights looking at all these different things,
Uh-huh.
but how does the model understand the order of the words?
Right.
Like if you change the order of the words in a sentence,
Yeah,
it means something totally different.
absolutely.
So how does it handle that?
That's a great question. And that's where something called positional encoding comes in.
Okay, positional encoding.
Positional encoding.
What is that?
So they basically add a special code to each word
Okay,
that represents its position in the sentence.
like a little address.
Like an address, exactly.
Okay.
So even though it's looking at the whole sentence at once,
Right,
it still knows where each word belongs
Okay.
in the overall order.
that makes sense.
And they use these things called sine and cosine functions
Sine and cosine
to
here.
create these positional encodings.
So like trigonometry.
A little bit of trigonometry in there.
Wow, they really thought of everything.
They did.
Okay, so we've got attention.
Yes.
We've got positional encoding.
Mhm.
Is there anything else we need to know about the architecture before we move on?
Well, the paper also goes into detail about what's called the encoder-decoder structure. of the transformer.
Encoder-decoder?
Encoder-decoder.
Okay.
It's a common structure for things like machine translation,
Right.
where you have an input sequence
Uh-huh.
and an output sequence.
Okay.
So the encoder analyzes the input,
Right.
and then the decoder generates the output.
Makes sense.
But instead of using RNNs, they use these stacks of self-attention.
Stacks.
Yeah, stacks.
Like pancakes.
Kind of like pancakes, yeah.
Okay.
And these point-wise, fully connected layers.
Oh, boy, now it's getting interesting.
Things are getting a little more complicated now.
Stacks of self-attention.
Yep.
This is where I think it really starts to get interesting.
Yeah, this is the heart of it.
So maybe we should unpack that a little bit more.
We should definitely unpack that.
I'm ready to go deep.
Let's do it.
Into those layers.
Awesome. So we left off talking about those stacks of self-attention in the encoder.
Yeah, those stacks are kind of blowing my mind a little bit.
Yeah, there's a lot going on in there.
So let's dig into those and see if we can unpack them.
So the encoder is made up of 6 of these identical layers.
6.
6.
Okay, so it's like 6 levels of analysis.
Exactly.
Each one building on the last one.
That's a great way to think about it.
Okay.
So each of these layers has 2 sublayers.
Okay.
The first one is that multi-head self-attention.
Right, that we were talking about.
That we were just talking about. So it's taking those words, comparing them to each other, seeing how they relate.
And the self-attention part means it's comparing words within the same sentence.
Exactly.
Okay.
So it's understanding the relationships within the input.
Not just understanding the words themselves,
right,
but how they connect to each other.
Within the context of the sentence.
Yes, exactly.
Yeah.
That's so cool.
It is.
And so that we've got these multiple heads.
Yes.
You're right.
We've got our multiple spotlights.
The spotlight.
Shining on different aspects of the sentence.
Okay, so we've got like one spotlight looking at the grammar, one looking at the meaning.
The semantics.
Yeah. That's pretty amazing.
It's pretty cool.
So it can really get this nuanced understanding of what's going on in the sentence.
It can.
Okay. So we've got this multi-head self-attention layer.
Yeah.
It's doing all this analysis. What happens next?
So after the multi-head attention, the output goes through what's called a position-wise feed-forward network.
Position-wise.
Position-wise feed-forward network.
Okay. That sounds a little complicated.
It's not as bad as it sounds.
Okay.
So basically, you can think of it as having a separate processing unit for each word in the sentence.
Okay.
And this unit takes the word's representation from the attention layer, and it just kind of refines it.
Okay. So each word gets its own little
mini analysis.
Mini analysis.
Yeah.
It's fascinating.
It is.
So it does the big picture analysis with the attention. And then zooms in on each individual word with this feed-forward network.
That's right.
Okay.
So we've got our multi-head attention. We've got our position-wise feed-forward network.
Yeah, this is great.
There are 2 more kind of important things that happen in each encoder layer.
All right, I'm ready.
That we need to talk about.
Hit me.
And those are residual connections and layer normalization.
Okay. I remember seeing those words in the paper.
Yes.
But I wasn't really sure what they were all about.
So residual connections, basically, it's kind of like when you learn something new, you build on what you already know.
Right.
You don't just completely forget everything you knew before.
Right. It's not like tabula rasa every time you learn something.
Exactly.
Okay.
So residual connections do the same thing for the transformer. They allow each layer to preserve information from the previous layer and just add to it.
So it's not overwriting everything.
It's not overwriting. It's just adding on.
Got it.
And this helps prevent information loss as the data is flowing through all these layers.
So it's like taking notes in the margins.
Yes.
Instead of rewriting the whole chapter every time.
That's a perfect analogy.
Okay, cool.
And then layer normalization.
Layer normalization. Yeah, what's that all about?
So normalization is basically like a balancing act.
Okay.
As the model is learning, it's adjusting all these parameters based on how well it's doing.
Okay.
But sometimes those adjustments can get a little out of hand.
Oh, so it's like it can overcorrect.
It can overcorrect.
Okay.
And that can lead to instability.
Got it.
So layer normalization basically makes sure that the values at each layer are within a reasonable range.
Okay. So it's like keeping everything in check.
Keeping everything in check.
So it doesn't go haywire.
Exactly.
Got it.
So it makes the training process much smoother and more efficient.
So we've got all these things happening.
We do.
In each of these encoder layers.
We've got a lot going on.
It's a lot.
It is.
It's like a perfectly choreographed dance or something.
It really is.
Multi-head attention, feed-forward network, residual connections, layer normalization.
And all of that.
It's amazing.
Happens 6 times.
6 times.
6 times.
Because there are 6 layers.
6 layers.
Okay, so it goes through this whole process 6 times.
Yep.
So it's really
It gets a very deep.
getting this deep understanding,
Yeah.
not just of the words, but how they relate to each other.
The relationships.
Where they are in the sentence.
The order.
Yeah, it's incredible.
It is.
So the encoder's doing all this work,
Yeah.
creating this really rich representation of the input.
Setting the stage for the decoder.
Okay.
Which is where the magic really happens.
Okay, so the decoder is next. Decoder is next.
This is where we actually generate the output.
That's right.
I'm ready. Let's go.
Let's do it.
Okay, so we've made it to the decoder.
Yes, we have.
This is where the magic happens.
This is where it all comes together.
So the encoder has done all the hard work, analyzing the input, creating this rich representation.
All those layers.
Yeah, all those layers.
All that information.
And now the decoder gets to take that and actually generate the output.
That's right.
Whether that's a translated sentence or, whatever it is we're trying to do.
Exactly.
So structurally, is the decoder similar to the encoder?
Very similar.
Okay.
It also has those 6 identical layers.
Okay.
Each one with the multi-head attention, the feed-forward network, the residual connections, layer normalization.
So all the same stuff.
All the same stuff.
But I'm guessing there are some differences.
There are definitely some key differences because the decoder has a different job to do. Right. It's not just analyzing.
Exactly.
It's actually creating something.
It's got to produce the output.
So what are those differences?
So one of the big ones is in the decoder, they use something called masked multi-head attention. Masked.
Okay, what is that all about? Why does it need a mask?
So think about it this way.
Okay.
Imagine you're writing a story.
Okay.
You can only use the words you've already written to create the next sentence.
You can't peek ahead.
You can't peek ahead.
At the end of the story.
Right.
Okay. Yeah, that makes sense.
So the decoder's kind of in the same boat.
Okay.
It can only see the words it's already produced when it's generating the output.
Okay.
So the mask basically prevents it from looking ahead.
So it doesn't cheat.
It can't cheat.
It has to generate the output.
Step by step.
Word by word.
Just like you would write a sentence.
Okay, that's a really cool way to think about it.
So this masking is actually done through a pretty clever trick.
Okay.
They basically hide the future positions, setting their values to negative infinity.
Negative infinity.
Negative infinity.
That sounds complicated.
It's a little bit of math magic.
Okay.
But it works.
So it can only see what it's supposed to see.
Exactly.
At each step.
It's like putting blinders on it.
I love that analogy.
Yeah.
Okay, so the mask prevents the decoder from cheating. But how does it know what to focus on in the first place?
So that's where another really cool feature comes in called the encoder-decoder attention sublayer.
Encoder-decoder attention.
Yeah, this is like a direct line of communication between the encoder and the decoder.
So it's like the decoder saying, hey, encoder, what should I be paying attention to right now?
Exactly.
All right.
So the decoder can focus on the parts of the encoded input that are most relevant to generating the current word.
So they're like working together.
They are.
Like a little...
It's a beautiful partnership.
Okay, so we've got this masked multi-head attention.
Yep.
We've got this encoder-decoder attention. And of course...
Then don't forget.
We've still got the residual connections.
We've got to have those.
And the layer normalization.
Those are important. Yeah. So all that stuff from the encoder is still happening in the decoder as well.
Okay, so it's like the same dance.
Same dance.
But with these extra little moves.
Extra little moves.
The masking and the encoder-decoder attention.
Exactly.
Okay, this is so cool.
It is pretty cool.
So once it's gone through all 6 layers of the decoder, what happens then?
So then the final output is transformed and processed to generate probabilities. Probabilities for each word in the vocabulary.
So it's like it's saying, based on everything I've learned, here are the most likely words to come next.
That's exactly right.
That is amazing.
It is.
So this transformer model, it's really a game changer.
It really is.
It's so much more efficient.
Especially with those long sequences.
Yeah.
It can handle things that RNNs just couldn't even dream of.
And it's not just machine translation either.
Right.
Like you said, it's being used in all these different areas of AI now.
Image recognition, music generation.
It's like it's opened up a whole new world of possibilities.
It really has.
It's incredible.
So this paper, it wasn't just about a new model.
Right.
It was like a whole new way, of thinking about AI.
It's amazing.
It's really cool to see how one idea can have such a huge impact.
Well, this has been an awesome deep dive.
It has been fun.
I feel like I actually understand the transformer now.
I hope so.
At least a little bit better than I did before.
Well, I think you did a great job asking all the right questions.
Yeah, I was just following your lead.
Well, we make a good team.
I think so, too.
So for all our listeners out there,
yeah,
if you want to learn more about the transformer, there are tons of great resources out there.
Definitely.
So keep learning, keep exploring. Yep. And who knows, maybe you'll be the one to come up with the next big breakthrough.
That's a great thought.
Yeah.
Well, thanks again for joining us on this deep dive.
It was my pleasure.
Into the world of the transformer.
Absolutely.
We'll see you next time.
See you later.